Kalavashit Reddy, pursuing my BTech at Institute of Aeronautical Engineering. Today we are going to be discussing about autonomous quadrilateral for accurate positioning. Uh, Generally, quadrilaters are robotic entities which usually hover in air. Uh, the main goal of quadrilaters is to reach from point A to point T in aerial direction using XYZ coordinates and accurately calculating the distances between 2 points and generally acquiring efficient directions from data processing. So how this process is happening, let us dive deep into this video. So quadrilaters, a key category of UAV, rapidly evolved due to their maneuverability and stable hovering, finding use in fields such as construction, agriculture, rescue, and surveillance. A major challenge in their operation is autonomous landing, especially under dynamic and uncooperative conditions. Traditional methods like vision-based landing rely heavily on markers or patterns, which can be limiting this work. Leverage a motion capture system, specifically OPTrack, to enable accurate real-time localization of both uh, the quadrilateral and a landing platform in complex environments. Unlike prior vision only systems, this approach eliminates the need for continuous visual tracking and marker dependency, enhancing flexibility and reliability. The overall problem can be classified into mainly three parts: localization of quadrotor and landing platform tracking and estimation of landing platform and safe landing of quadrilateral on a stationary or moving platform. The 3D reference coordinator frames are attached to center of gravity of quadrilaters and the landing platform has x of q, which is the stationary point, and x of p, which is the dynamic part, respectively. The mobile platform frame of reference is positioned with an offset of 9 centimeter of the ground. The overall operation is considered successful when quadrators manage to land on target platform. The three problems introduced earlier are defined as follows. Problem 1: localization of quadrilateral and landing platform. Build up a framework consisting of a quadrilateral platform and four opti camera to localize the ground, vehicle, and aerial to obtain XP and XQ in real time. Problem 2: tracking and estimation of landing platform. The quadrilateral tracks the uh, landing platform. The study utilizes the DIJ Telo Edu, a lightweight programmable quadrilateral uh, of 87 grams with dimensions of 9.8 cm into uh, 9.525 cm into 4.1 cm. It supports multiple programming languages such as Python, Scratch, Swift, and MATLAB via SDK, offering flight time of 30 minutes, a speed limit of 8 meters per second, and a maximum flight height of 30 meters. The landing platform measuring 30 cm into 30 cm is mounted on a differential uh, drive robot with a maximum velocity of 0.8 meters per second. So here we can see that a quadrilateral, here we can see a quadrilateral and a platform which are at its reserved position, which is used to track how much distance is going to be calculated using XYZ coordinates. Now, the linear velocity of quadrature in a body fixed frame is defined using VB, that is equal to UVWT belonging to R of 3, whereas V is equal to X bar of Q into Y bar of Q into Z bar of Q. Transpose belonging to R of 3 is used to represent its velocity in inertial frame, which is placed globally. The linear velocities are related by rotation matrix are as follows. R function of phi theta psi belong to SO3 as V is equal to RVB, where R is a rotational factor. Here, uh, Euler angular notation matrix R, which is notating. So, R is equal to the rotational matrix, which is associated with the angular velocity, which is P of omega B, which is associated with torque, which is derived from force B, and mass G, that is equal to summation of Jp omega G into E cap of 3 minus 1 I plus 1 omega I. The Kalman filter serves two purposes: tracking and estimation of a mobile platform position and velocity. Assuming that the mobile platform can move in a 2D plane, its notion can be defined using translation along x-axis, y-axis to track mobile platform. The position information must be at every instant the Kalman filter. So the final Kalman filter equation is x of k plus 1 is equal to ax of k plus pu of k plus w of k. So only the position and attitude of quadrator are available through motive and are either streamed to the ground control station or recorded as log data. So the final equation will be W of n is equal to nu of I W raw into n of I. So the model predictive controller is responsible for determining the desired control inputs to reduce the error between the trajectories of quadrators and the platforms. These processes is performed by solving the constrained tracking problem between and minimizing the performance index of optimization problem. The manipulated variable is computed using quadratic programming optimization. The quadratic op So this is the actual model where MCS motion capture sensors and Kalman filters ultimately result in quadratus rotation and movement, and the experimental results can be before initiating the experiment. Calibration is performed for MCS by tracing the motion sensor markers using motives. As you can see here, the PoE switches and the quadrators exchange data through LAN and Wi-Fi, and the pre-processing is done in PC itself. So for this experiment, the straight line distance between LAN platform and the quadrators is defined as 71 cm. Now coming to the results, as you can see, the quadrator successfully traces a stationary point by resting, taking off, tracking, and landing. Moreover, this is the uh, 3D representation of how uh, actually the quadrator lands on platform. And now this is the dynamic platform where the quadrator uh, landing platform is rotating and quadrator figures it out. In conclusion, the study a quadrator uh, a quadrator usually requires a Kalman filter, a predictive controller, and a motion capture are used to design such systems.